Okay, so backside of your 11.3 notes, we're now working with surface area of cones. Cones have two surfaces, okay? Their bottom is a circle, okay? And then that lateral area, that lateral surface is, well, the cone part. I call it the waffle portion of the cone because I really like ice cream. And so it's the waffle portion of my waffle cone, all right? Okay, so the question now is, of course, how do we find the area of the waffle portion? So let me show you where that comes from. First off, let's again talk about a little bit of vocab. Cones are still going to have a slant height, okay, just like pyramids had. They also, of course, have the total height of the cone, which is capital H. Area of the base there. The cones have a radius, of course, and a vertex. So there's all of our pieces. Now, let's imagine for a moment that rather than working with a cone, because I want to build up to the cone, essentially, okay? So first off, let's say that I have a triangular pyramid, okay? So again, I'm thinking in terms of a cone. I want to find that lateral area, that waffle portion, which is this part here, okay? But the base, rather than being a circle, is now a triangle. So how many triangles are on that lateral surface? On this one? 3 on the lateral surface, not the base. Lateral surface does not include the base. There are 1, 2, 3 triangles because I had a triangle base. And so if I was trying to find my lateral area, I would say 1/2 base times height plus 1/2 base times height plus 1/2 base times height, because I have 3 triangles. Now I realize that technically I could say 3 times 1/2 base times height, but I don't want to do that right now. Okay? All right. But let's say, okay, wait a minute. We're working up towards a cone. So I don't want a base of a triangle. I want a base of a square. Okay. So envisioning the lateral area is this. How many triangles are on the base of this guy, or around the lateral area of this? 4 now. Okay. So that means in my equation, I need to add on another triangle. Okay. Well, rather than having a square base, let's say it was a pentagon base. Okay. Again, we're now working towards more of a cone-looking shape. How many triangles are there for the lateral surface? 5. Oh, I need to add on another triangle. Okay. Oh, wait, I don't want a pentagon. I wanted a hexagon. Okay. How many triangles do I have? 6. Okay, got to add on another one. Okay. So let's say that I'm going to walk around with the cone here for a moment. Because if you look really close at this cone, maybe you don't have to look that close, but I'll still walk around. You know, because they couldn't actually make a smooth waffle surface on this cone, it's kind of cut into little triangles, okay? So I'm going to walk around a second, make sure everybody can visualize all those little triangles on there. Okay? Everybody see all those little cuts in there so you can see those little triangles? You know what I'm talking about? Everybody okay? Good, good. All right. So let's say, and I haven't actually counted, but let's say there's 20 of them. There's 20 little triangles on there. So that means the base of this would actually be a 20gon, right? Okay, so that means I have 20 triangles. So I'm going to add on 20 more triangles. Okay, did it. Added on 20 more triangles. Or actually, I added on 14 more triangles. All right. So now, rather than having a 20gon, let's say I have a 100gon on the bottom. So now how many triangles are there going around the top, or going around that lateral surface? 100 of them, right? What about 1,000gon? There's 1,000 triangles, or 1,000,000gon. There's now 1,000,000 triangles. But what would happen to the length of the bases of those triangles? The more and more triangles I have, the smaller and smaller those bases get. And if I actually had 1,000,000gon in front of me, do you really think we'd be able to tell that it was 1,000,000gon? No, it would probably look like A circle, right? Okay, so let's look at this equation now. We have our million-gon equation written up here. So what do you notice is the same about each part of that equation? They're all 1/2 base times, so each and every one of them has a 1/2 in it, right? I'm going to factor that 1/2 out. Remember factoring from Algebra 1? You can pull that number out in front. Each and every one of them has a height that's the same, right? Because all the triangles are going to be the same height. So that's going to be the same height. Okay, and then what's left inside but all the bases of those triangles added up? Okay, so I've got a million little bases added together. So let's look back at the hexagon for a moment. Looking back at that hexagon, if I add up all of these bases of my triangle, if I add up all those bases, what am I actually getting on the hexagon? What measurement is that? Perimeter. If I add up all the bases, that's the perimeter of the hexagon. And so if I take my 1 million gon and I add up all the bases, I'm still finding the perimeter. But remember, in our million gon, if we're looking at a million gon, you're never going to tell that it's a million gon. It's going to look like a fuzzy circle, basically, right? You're not going to be able to tell that there's actual little line segments there. It's going to look like a circle. Well, what is perimeter of a circle? Circumference. So all of this is just circumference. And by the way, height is the height of the triangles. We didn't call it height of the triangle yesterday. We called it what? Altitude was the height of the whole pyramid. Slant height. And so our equation now becomes 1/2 L times 2 pi r. Slant height is the height of our triangles, and circumference is all of those bases added together. Well, what is 1/2 times 2? 1. That goes away. That cancels away. And so our lateral area, which I am calling the waffle, is pi r L. That's how you find the lateral area of a cone.
Waffle sounds so good.
A waffle does sound very good right now. Okay. All right. Questions? Pi r L. That's the waffle portion of a cone. Pi r L. Okay, excellent. So let's try a problem here. So taking a look, we have a cone. Cones have how many surfaces? 2 surfaces. The one on the bottom is a circle, which ours has a radius of 15. And then we got to add to it the other surface, which is the waffle. Okay.
Would it just be like another circle?
All right, so our circle, how do we find the area of a circle? Pi r squared plus the waffle, pi r L. So we have pi times our radius is 15 squared plus pi times our radius is 15 times the slant height, which is 25. Okay, so let's see here. 15 squared is 225 times pi plus what's 15 times 25? 375 times pi. So that means our surface area is going to be 600 pi square centimeters. Questions? Okay, then what I would like you guys to do is to try this example on your own, but please be careful in the fact they do not give you the slant height. You need to find it. Okay, so your correct answer here should be approximately, if you went to all the way to an approximate whole number, it would be 46 square feet. The exact answer is a big confusing looking thing. So let's talk about how to get that exact answer. So we have a circle, or two surfaces. We have a circle that has a radius of what? 2. Plus the waffle portion of our cone. And so that means our surface area is going to be pi r squared plus pi rl. So pi times 2 squared plus pi times 2 times the slant height. Well, we need to find our slant height, so we need to look at this triangle. Okay, so we have that tall part there. The height is 5. This radius is 2. And so I'm going to use 2 squared plus 5 squared equals my slant height squared. So 4 plus 25 is 29. And if I take the square root of both sides, I find out that my slant height is the square root of 29, which I need to leave it as the square root of 29 because I don't want decimals yet. I need an exact answer. And the square root of 29 can't be simplified. It can't be reduced. That's it. So we plug it in up here. All right, so 2 squared is 4 times pi plus 2 pi times the square root of 29. I can't add the 4 and the 2. Even though they both have pi next to them, 2 pi is also multiplied by the square root of 29. So before I add, I have to do all that multiplication. And so this is as far as I can make it. If they asked for an exact answer, this is my exact answer. Because I can't simplify it any farther. Now, if they ask for us rounding this to the nearest whole number, then of course we plug that into a calculator, and we would be able to find out that our surface area is approximately 46 square feet if we're rounding to the nearest whole number. Okay? Questions or comments on that example?
So if you were to switch around pi and the square root of 29, would that be wrong?
Okay, let's talk about that for just a moment. Some countries still write their math this way. The U.S. has gotten away from it a long time ago, okay? What I'm talking about is the square root symbol. Let's not do it in gold. The square root symbol used to have a little tail on it that would say the square root is stopping here. And so I could then take 25 and put a 2 back here, and I know that I'm actually taking 5 times 2, the answer is 10, rather than thinking I'm accidentally taking the square root of 252. Okay, these put a little tail on the end. But we've gotten away from that notation, and in fact, we always now put the square root behind our numbers so that we know exactly what is in the radical symbol. Okay, so there's no confusion when we're writing stuff. And so when I do that, even though usually I like the pi to be at the end, I'm going to put the pi in front of my square root. Just like variables, I say 5x. But if my whole number, or my number out in front of my variable, is a square root, I'm going to say x square root of 7. I'm going to put the square root after it because I don't want it to be confused with the square root of 7x if I put it after. Okay? So, yes, square roots should always be written last. All right?